Okay, so this next series of videos is going to be about systems of first-order homogeneous constant coefficient linear recurrence relations. In other words, things that look like this. This is just a 2x2 example, but you could do higher order examples. You could have fn plus 1, gn plus 1, hn plus 1, etc. So the idea is you have these two functions of n, fn and gn. They're defined recursively, but they're also tangled up. And so the goal is to find out what is f of n and what is g of n. So before watching these videos, you're going to need to know a little bit about matrix operations like matrix addition, subtraction, identity matrices, matrix multiplication, and a little bit about eigenvalues and eigenvectors, although I think I'm going to do some review videos on that, and diagonalization, which I'll do a review video on. And aside from that, it's helpful to know a bit about the linear recurrence relations, which I have a whole bunch of videos on. So from here, what you can do is you can write this as a matrix equation. If I have a vector containing fn plus 1 and gn plus 1, then I could write this as the matrix product of this matrix containing the coefficients a, b, c, and d, and a column vector containing fn and gn. And so I'll just introduce some notation here that I'll use throughout the next videos. I'll call this matrix capital A, and I'll call this column vector here fn with an arrow on it. So this is the vector containing fn and gn. And then that just makes this one over here fn plus 1, the vector. So this is a much more succinct way of writing this same thing. Okay, so like I said, the goal here is to solve for what is fn and gn. And so one way we can do that is we can look at ones that we already know how to solve. And in fact, there are a lot of them that we already know how to solve. Let's look at a linear second order recurrence relation, homogeneous, etc. The ones I've been talking about in the last videos. Something like this. We can actually get this in the form of a 2x2 system of first order equations. So here's how you do that. First of all, I'm assuming that A is non-zero, otherwise if it were 0 we would be talking about a first order, and that would be pointless. So let's assume A is non-zero, and then let's divide by A. So you get this. So one thing to notice here is that this is actually, even though there are 3 constants here, this type of equation actually only depends on 2 constants. It only has 2 degrees of freedom, this type of equation. But anyway, so let's define g of n. So let's let g of n be f of n plus 1. And so what this is going to do is it's going to allow us to write this in this type of form here. If g of n is f of n plus 1, then that would make g of n plus 1 f of n plus 2. So I want to write this in kind of like this original form here to see what's going on at first. So I have f of n plus 1. I know that this is just equal to g of n. And now g of n plus 1, well, take a look at this second equation here. This is g of n plus 1, this is g of n, and this is f of n. So if I took these two terms and subtract them to the other side, then what you get is minus c over a f of n minus b over a g of n. And so now, this is my 2x2 system of first order equations. I could write this as a matrix equation, so I could put like this. Here the coefficients are 0, 1, minus c over a, and minus b over a. And then, so the interesting thing here is we actually know how to solve this one. Since it comes from this original definition here, we know what f of n is. Let's assume that there's no repeated roots in this case. So f of n would just be c1 lambda 1 to the n plus c2 lambda 2 to the n, assuming no repeated roots. G of n, this is just f of n plus 1. So I can just replace this n with n plus 1. And so I'm just going to write it like this. And so this is the solution. So one last thing I'd like to do in this video is write this in matrix form. So my f of n vector, this is equal to, I could say this is c1 times a vector containing 1 and lambda 1 times lambda 1 to the n here. And then over here, I have c2, a vector containing 1 and lambda 2 times lambda 2 to the n. This is actually kind of significant because what we've seen is that if we start with a second order equation, the solution, we now know what the solution to the matrix equation looks like, or the solution to the system of first order equations. So it's kind of a leap, but what we could do is assume that in general that these matrix equations have solutions that have this type of form: arbitrary constant times a vector times some constant lambda to the power of n plus another arbitrary constant times another vector containing some constants and another number lambda to the n. So that is kind of a jump, but if we use that reasoning, then we can figure out what those numbers lambda and what these vectors must be, and we can find our solution that way. Before we do that though, I'm going to make the next video about the superposition property. It's very similar, or it's pretty much exactly the same to with the second order equations, or nth order single equations, not systems, where you can just take scalar multiples of different solutions. As it's going to turn out, this is a solution to the system, this is a solution to the system, and so any scalar multiple is a solution. Then the last thing I want to say is that, so we saw that any one of these second order homogeneous equations could be written as a 2x2 system, but the converse of that is false. Any 2x2 system, not every 2x2 system can be written as a second order equation like this. So, and I'm not actually gonna give a proof for that, but it is, here's a reason why it's kind of intuitive. If you look at this second order equation here, like I said, there's only 2 degrees of freedom. You have these two constants here controlling it. But in general, with a second order system, you've got this entire matrix of like 4 coefficients there. So anyway, yep, watch the next video.